There have been many other experiments, such as the one at my alma mater, University of Arizona, showing the dilation of time. In the experiment, they brought one clock to the highest peak in its vicinity on Mount Lemmon and the other at a hotel in the city of Tucson. The elevation of the clock at the hotel was 775 meters, about 2,540 feet, and the elevation of the clock at the summit was 2,780 meters, about 9,120 feet. So the difference in elevation was 2 kilometers, about 6,580 feet. The clocks measured 21 nanoseconds apart at the end of the 23 hours. This was proof positive that time dilation occurs, but not proof that the wavelengths are shorter or longer on the basis of distance traveled. The CfA Redshift Survey was the first attempt to map the large-scale structure of the universe. It began in 1977 with the objective of calculating the velocities of the brighter galaxies in the nearby universe by measuring their redshifts. The second survey, CfA-2, was started in 1985 and measured the redshifts of 18,000 bright galaxies in the northern sky by 1995. Another, the 2DF survey, conducted by Anglo-Australian Observatory with 3.9 meter Anglo-Australian Telescope between 1997 and 2002, covered an area of about 1,500 square degrees, surveying 221,000 redshifts and regions in both the north and the south galactic poles. The name derives from the fact that the survey instrument has a 2-degree diameter field of view. Also, the ROSAT all-sky survey observations performed between June 1990 and August 1991. Another, more famous survey was the Sloan Digital Sky Survey, Part 1 through 4, in which data collection began in 2000, and the final imaging data release covered over 35% of the sky, with a photometric observation of around 500 million object and spectra and over 1 million redshifts for more than 3 million objects. The main galaxy sample had a median redshift of Z equals 0.1. There are redshifts for luminous red galaxies as far as Z equals 0.7, and for quasars as far as Z equals 5. The imaging survey has been involved in the detection of quasars beyond a redshift of Z equals 6. The largest current surveys are the Deep 2 Redshift Survey and the VMOS VLT Deep Survey VVDS. These have recorded around 50,000 redshifts each and are mainly focused on galaxy evolution. The Deep 2 survey, or Deep 2, was a 2-phase redshift survey of the redshift Z is approximately 1 universe, where Z equals a measure of speed and by its extension the distance from Earth. It has used the twin 10-meter Keck telescopes in Hawaii, the world's second largest optical telescope, to measure the spectra and hence the redshifts of approximately 50,000 galaxies. The Z-Forge, or the 4-Star Galaxy Evolution Survey, is a large and deep medium-band imaging survey which aims to establish an observational benchmark of galaxy properties and redshift of Z is greater than 1. The survey is using near-infrared 4-star instrument on the Magellan telescopes. Another sky survey that concentrated on the CMB was the Wilkinson Microwave Anisotropy Probe, operating from 2001 to 2010. This measured temperature differences across the sky. According to the Planck satellite, the universe has expanded and cooled greatly. Due to the expansion of space, the wavelengths of the photons have grown. They've been redshifted to roughly 1 millimeter, and thus their effective temperature has decreased to just 2.7 Kelvin, or negative 270 degrees Celsius, just above absolute zero. Today, the CMB radiation is very cold, only 2.725 degrees above absolute zero. according to nasa.gov. Also, the Laser Interferometer Gravitational Wave Observatory, LIGO, first detected gravitational waves in 2016. Gravitational redshift is oftentimes cited by the scientific community as a force that affects light as it either travels away or toward a body, and the potential energy is denoted by P equals G mass 1 times mass 2 divided by distance squared. These forces are hard to measure on Earth except possibly at high altitudes, detecting a difference in gravitational fields and hence different redshifts to those fields. The most notable redshift quantifiable data is in sky surveys where gravitational lensing is said to be observed. To test gravitational redshift, one could bounce a radio signal to the moon and observe its behavior. This is how they calculate the distance of the moon. It is my hypothesis that the radio signal would come in clear with no delay and acknowledgement of redshift from a wave standpoint, but possibly after leaving the Earth's gravitational pull and entering into the moon's gravitational pull and back, it would undergo a gravitational redshift. Gravitational waves carry a signal that shows their redshift in mass, space.com. Gravitational redshift is a quantifiable result that is measured in many experiments. However, redshift of long-distance light patterns has not yet been corroborated. Another observation discrepancy causation culprit of redshift is that these frequencies are challenging to test for due to our own understanding of wave theory and the large distance of the galaxies. There would be no way to bounce a signal or observe the wave's orientation to the signal that far away in space. The thought experiment comes to mind to show gravitational lensing that if, say, a radio signal was sent by an emitter on the other side of the sun and the sun's large gravitational pull bends the radio wave, would the information in the radio wave be distorted? In my estimation, it would be. However, when not interacting with a massive body or gravitational pull in space, the information in the wave would be preserved and not perturbed in any way, just like radio and TV waves are not impeded or changed by any observation point on Earth. Like Newton's first law states, every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. An object, meaning massive body, has the ability to change the orientation of the wave and the information inside of the wave. Without the massive body, the light or wave will remain unchanged until it interacts with another massive body. Cosmologists may say the lack of redshift in radio and TV waves is not a function of distance but a function of velocity. This can be refuted by what we see daily as moving cars changing their velocity, moving away from a mission tower, emitting a certain radio frequency. If that hypothesis is correct, the car's radio would need to constantly change its frequency and adjust to account for the redshift every meter or so. If you would relate this concept to the Doppler effect of comparing, say, a siren changing pitch as it moves by the observer to a radio wave being broadcasted by a station, the radio wave would not change its pitch or frequency as you send it across the sky from the emission tower to your receiver in the car at all. After that critical point in which the radio signal is turned into sound and exits in the speakers, that is when the Doppler effect would take effect and be integrated into the wave, and an individual at rest listening to the radio broadcast as the car goes by, the pitch would be lowered. Even in sound, as it relates to redshift, I'm not sure we as humans understand fully the concept of the Doppler effect. In the case of an object with its radio on relatively loud with the sound of two guitarists playing a series of quarter notes at 440 Hertz moving towards us, it is said that the Doppler effect is caused by increasing the sound's frequency and bringing the sound waves closer together, causing a higher pitch. However, if you would take the example of two guitarists strumming the same chord, but instead of quarter notes, there were eighth notes, the frequency doubled, per note, yet the pitch stayed the same and was not affected by the Doppler effect. There would be no increase of frequency or raising of pitch. The two guitarists would register the same pitch. The frequency of waves reaching the observer's ear would be increased. This would lead one to believe that just because the two vibration waves are closer together or more frequent, this does not raise or lower the pitch. It is my hypothesis that the Doppler effect in sound is caused by the motion of the object and velocity of the emitting body comparatively to the rest body. I do not have any scientific evidence to apply that idea to.